Welcome to our last segment of Chapter 8, the Basics of Chemical Bonding. So we left off with this idea of a coordinate covalent bond. So if we take a look at ammonia here, ammonia has normal covalent bonds. We have 3 hydrogens, each with a single electron, nitrogen willing to accept those 3 electrons, right? So 1 electron from each must be shared between the 2 atoms. And of course, we get ammonia. Okay. Now, how does this fit into coordinate covalent bonding? Well, it's this lone pair right here. Okay. That's going to play a part in the coordinate covalent bond. So when we make ammonium, we'll notice that H plus has no electrons. We represent H plus as an acid. So we have H plus. So if we mix an acid into solution with ammonia, ammonia we know is a base. And the lone pair on the nitrogen will accept that hydrogen. Now remember, that's a proton with no electrons, which means it could accept 2 electrons to complete its octet. So it can still get the 2 electrons shared between the 2, the lone pair on the nitrogen and the H that was H plus with no electrons. That is our coordinate covalent bond. So both electrons of a shared pair come from just one of the 2 atoms. That is the coordinate covalent bond. Once that bond is formed, it acts just like any other covalent bond. So you can't tell that the 2 electrons only came from the 1 atom. We can't tell where the electrons came from after that bond is formed. So it's useful in understanding chemical reactions. Another place we see coordinate covalent bonds is when we're dealing with boron. We've already pointed out that boron is electron deficient. And so here, the nitrogen can donate the lone pair to the boron, forming a single bond. And of course, it's a coordinate covalent bond, as both electrons came from the nitrogen. All right, so draw the best Lewis structure for the following. So HClO4. What's going to be the best Lewis structure for that one? Once you're finished that one, try XeF4. And then I3 minus. And last but not least, BrF5. Okay, so you want to pause here. Go ahead and work those 4 compounds out. And then once you hit play, we'll start to go through some of the answers here. All right, so HClO4. So chlorine here is actually going to act as our central atom. Put 4 oxygens on here. Okay, so that's our skeletal structure. And so we have 1 plus 7 is 8. Then 6 times 4 gives us 24, which means we have 32 electrons. We've used up 2, 4, 6, 8, 10, so we have 22 left. Gonna make this guy happy. Gonna make this guy happy. Gonna make that one happy. Gonna make that one happy. And that one's already happy. This one already appears to be happy. So you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. That's our 22 electrons. Everybody's completed their octet, and so this looks like this would be the best structure. Now we have a -1 formal, -1 formal, -1 formal, 0, 0. Now what's our chlorine? Well, we have 7 minus 4. That would be a +3. A little weird, but we've got the -1 on all of the proper oxygens. And let's see, can we share a pair? So if we share a pair of electrons here, right, that would bring this down to 0. This would then be +1, excuse me, +2. And we'll share a pair here. I'll break this one to 0. And then this one would be +1. and then I could share another pair. That would give me zeros all the way around. Does that make sense though? So we have chlorine in the middle with a double bond to an oxygen, double bond to an oxygen, double bond to an oxygen, bond to an oxygen, bound to a hydrogen. Now chlorine has 1, 2, 3, 4, 5, 6, 7 bonds, which means everybody has a formal charge of 0. As that is, this is our best structure. All right, how about XeF4? Next, I'm going to erase. Give ourselves some space there. All right, so XeF4, so we're going to put Xe in the middle. Draw out the fluorines. All right, so let's see, we have 8 plus 7 times 4 is 28, so we have 36 electrons. We just used up 2, 4, 6, 8 of them. Puts us back at 28. Put on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 2, 4. So minus 24 electrons. Leaves us with 4. Well, at this point, everybody's happy. However, we have 4 electrons left over. So what we're going to do is we're going to add 2 lone pairs to the Xe. Now, why the Xe? Well, remember, the xenon has a D shell. So it can actually have an extended shell. We can put those electrons there, and that's going to be okay. We cannot give them to the fluorine. The fluorine does not have a D orbital, and so it can't accept anything over the octet. So, strange again, I know. All 4 of these are going to be a little bit odd, breaking a few of the rules, but fitting other new methods we kind of learned just recently. All right, so let's go ahead and erase that. All right, so back to I3 then. So I3, so we'll go 1, 2, 3. We know the whole thing. It's going to have a -1 charge. We have 22 electrons total. All right, we have 7 times 3 is 21 plus the charge. So that's where I got the 22. We just used up 4, which means we have 18 left over. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12. It's going to leave us 6 electrons. Uh-oh. What are we going to do with these? Well, since this iodine is the central iodine and everything's connected to it, we're going to just to pretend or assume that it's going to take on all the excess electrons. So we're going to go 1, 2, 3, 4, 5, 6. Again, odd, I know, but here we're going to use our d orbital. We're going to go to the extended here, take those extra electrons in, so we have 2, 4, 6, 8, 10 electrons around this iodine, leaving this iodine and this iodine to have formal charges of 0. All right, one last one to go here. Our last one here is Br F5. So we're going to go 1, 2, 3, 4, 5. Put our fluorines in. So we have 7 times 6 for our electrons. So it means we have 42. 2, 4, 6, 8, 10 just got used up. Now we're going to make everybody else happy. There's 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's 20, 22, 24, 26, 28, 30. Means we have 2 left over. We're going to put those 2 on our bromine once again. Again, bromine does have a d orbital. That gives it 2, 4, 6, 8, 10, 12 electrons in its outermost level, but that's all right. It can hold up to 18. So that's going to be okay. Again, those are some of the oddballs that we would see. I would not expect to have that entire grouping on your exam, but you should be prepared probably for one of them because we will have to explain coordinate covalent bonding and excess electrons. Both are very common. All right, the last things that we hit in this course, for this chapter rather, is going to be carbon compounds. We've talked about them a little bit in previous chapters. Carbon-containing compounds exist in large varieties, mostly due to multiple ways in which carbon can form bonds. There are functional groups. These are groups of atoms with similar bonding, commonly seen in carbon compounds. Molecules may contain more than one functional group. So whenever we're looking at like anything in the news when it comes to drugs, for drug testing, things of that nature, and I'm talking about medicinal purpose drugs, not illegal drugs, but like Pfizer, Merck, Moderna, a lot of these companies are in the news right now looking for the vaccines. So these types of molecules typically have more than one functional group in them. Okay, and so what a functional group is a pattern of atoms around the carbon that will then react in a very specific manner. So important compounds of carbon would include alkanes. So these are going to be our base chains. These are all hydrocarbons. They only have single bonds. So it'd be like methane, ethane, propane. There'll be a topic called isomers. So we have the same molecular formula, but things are connected differently. So for instance, here you can see we have butane. So the formula here is C4H10. Over here we have isobutane, or if you prefer 2-methyl propane. We still have 4 carbons and we still have 10 hydrogens, but what we've done is taken one of the hydrogens off and kind of moved it into the middle of the chain. And so now we have 3 carbons in a row with one single carbon sticking off of it. These are called isomers, and we can have different styles of isomers. These are structural isomers. Now, those are not actually going to be functional groups. Functional groups are going to be when we see, again, a different pattern. So for instance, alkenes. So now we're going to contain a double bond. So we'll have a carbon-carbon double bond. Now this double bond is a reactive center. And so that's going to be a site for reaction. That's ethylene. We also have butene. Okay, so now we have the 4 carbons, but now we have a double bond in it. Alkynes is another functional group. Here we're going to have a triple bond. So this would be like acetylene. And so what you might know already is acetylene burns hotter than propane, right? It gives off more heat in that reaction. And this should make sense now because we have that triple bond. That's a more energetic bond. So when we combust acetylene, we get more energy out of breaking that triple bond and rearranging it and making more CO2. And so that's going to burn hotter, if you will. Right? Now there's also oxygen-containing organics, for instance, like alcohols. So what we'll do is we'll replace an H with an OH group. So for instance, here's our drinking alcohol. This is ethanol. We have ethane, but then we pulled the hydrogen off and replaced it with an OH. Okay, now this is not a base. So a lot of times when we see hydroxide, when we see that OH in general chem, it's usually a base. Here, this is not basic. Okay, this is not basic at all. The OH does not act like the OH of a base. We have ketones. Ketones means we're going to have a carbonyl group. Okay, so the carbonyl group is the C double bond O. And so a ketone is going to be that carbonyl group along the carbon chain where we have the carbon chain continuing. So the carbon chain is going this way and this way. Now, carbon and a hydrocarbon with a double bond to oxygen. We could also have an aldehyde along with that ketone. The aldehyde simply means the chain doesn't keep going and that the hydrogen is actually going to end the chain at that carbonyl group. So for instance, this would be our carbonyl group, the C double bond O. And then depending on what is here, and we use R's to represent that. So R's could be any alkyl group. When we have those R groups, depending on what they are, will determine which one of these functional groups we actually have. Okay, if it's an aldehyde, that means one of those endings has to be a hydrogen. So you can see hyd, hydrogen. Means we end on a hydrogen right next to that carbonyl group. So it could be two hydrogens, but at least one of those has to be a hydrogen. So if we think of this as position 1 and position 2, one of these two has to be a hydrogen. Organic acids, we'll see that carbonyl group. Right? So there's the carbonyl. They stick out like sore thumbs. We see that, and then we have an OH group. So we have the alcohol next to the carbonyl. That's going to be an acid. Now we can also have nitrogens in our organic compounds. And so that means we're going to have amines. So amines simply means we have single bond nitrogens in there. So here we have a carbon to a nitrogen, and then the nitrogen has two hydrogens. That's fine. That's going to be a primary amine. We use a 1-not. And then you could have nitrogen here where we have dimethylamine. So now we have two carbons connected to the nitrogen and only one hydrogen. We call that a secondary amine. And of course, we could replace this hydrogen, and that would give us what we call a tertiary amine. So we could have primary, secondary, or tertiary amines. All right, so how many isomers are there of butanol? Now, this is a question I would not ask you on a test. Our focus is not on organic chemistry. For some of you, you might have to go on. I know there's a couple of you each semester anyway that are visiting us and are trying to work towards a PA or an MD, or maybe you're going for dentistry or vet school or something along those lines. And that professional school has told you you need to pick up 4 semesters of chem, which is usually Gen 1, Gen 2, Org 1, Org 2. This is getting into the organic section, which is actually my preference, but that's what all of my studies were in as a student myself. I was organic synthetic by trade, but that's not going to be important to you in Gen 1 and Gen 2. So we're not going to spend a whole lot of time worrying about isomers of butanol, right? So of butanol though, so if you have 4 carbons, the way we would do this problem, and we know that we have to have an OH on here somewhere, so I'm going to put an OH right here. Right, so that would be one isomer. Now, we're talking about structural isomers. The rest of these would be hydrogens. I'm not going to take the time to fill all that in. You can do that yourself. Right? A second one would be just moving that OH group around. So now I'm going to put that OH group on this one. Excuse me. And at this point, we would have the same number of hydrogens, but the oxygen is in a different carbon. That makes them isomers, structural isomers. You can usually tell by naming. So this would be 1 butanol. This would be 2 butanol. Now, I know what you're saying, just do it again, move it over one more. But if I move over one more, what happens is we just count from the other direction, and that would also be 2 butanol. So those are my only 2 isomers out of the, what we call the straight chain. But the next thing I can do is make that chain shorter and go to that methyl group we talked about before. And now I only have 2 places here as well to put my butanol. So I could put my OH here on the 1. So now this becomes 1 butanol, but it's 2 methyl. So it'd be 2 methyl, 1 butanol. Or I can move the OH to the second carbon here so that they're both 2s, which means we have 4 isomers. But again, I'm not going to ask a question like that on your exam. So for this chapter, I would not be worried about that. What you want to focus on are drawing Lewis structures. So you should be able to draw Lewis structures for these organic compounds. And you should recognize that whenever we have carbon-carbon double bonds and carbon-carbon triple bonds, or if we have that carbonyl, the C double bond O, that we open ourselves up to resonance structures. And that's more likely where I'm going to go with those. All right, which molecule contains a carbonyl group? Hint, draw the Lewis structures to help decide. So first off, to have a carbonyl, we know we have to have a C double bond O, which means we can eliminate B and C as they do not have oxygen. All right. And hopefully you've come up with E. So for A, this could be an ether, or it could be the alcohol, right? So it could be ethanol again, CH3CH2OH. This is an amine. This is an alkyne. Again, no oxygens, so it couldn't be the carbonyl. Here we have an alcohol, so it's CH3OH. Last but not least, we have the aldehyde. All right, so that finishes up this chapter. And again, the focus as far as the organic pieces would be drawing Lewis structures and doing the dot structures for those, paying attention to resonance structures, being able to calculate formal charges. Moving forward, that little bit of organic you will need, we'll be talking about hybridization soon. Typically we use carbon for that because we're going to talk about sp hybridization in the next chapter. And so those organic compounds, I'll be sticking around, but I don't want the focus to be organic. We want the focus to be understanding bonding. Okay, so keep that in mind. If you have questions about anything in the chapter, I know I say this all the time when we're live, but again, ask. Don't be afraid to ask. Ask me anything. Even if it seems like a dumb question, it might not be as dumb as you think it is. And even if it is a dumb question, it doesn't matter. It still needs to be answered. And I'd be more than happy to answer them for you. So get a hold of me if you need help. Come to a student hour or schedule an appointment. All right. Talk to you soon for the next chapter.